So welcome everyone. Very happy to have you all here. This is the June version of the Architects Declare Lunch and Learn session. And before we get started, I would like with acknowledging the country where I'm calling from. It's the Gayamagal land in the northern beaches of Sydney. And I would also like to acknowledge the country where all of you are calling from today. My name is Valerie Saavedra, and I'm on the National Steering Committee of Architects Declare, and I work for BBN Architects as their regenerative practice lead. And today we have the privilege of welcoming Paul Stoller. Hi, Paul. And he's the managing director of Atelier Ten, Australian office, and the global leader of its benchmarking practice. He's recognized for environmental planning and design consulting work on large-scale campus, cultural, and urban projects. His projects notably balance daylight, thermal comfort, and energy efficiency to exceed client benchmarks and expectations. So he's the absolute expert in what we're going to talk about today, which is design, evidence-based design for passive performance. A topic that's extremely relevant today, not just in line of the current climate crisis, but also the current energy crisis that we're going through and the increasing cost of energy. So Paul will give us a hand to show us some base case principles that we all as architects can implement in our day-to-day design, and also though how we can implement this through some design analytics as well. So over to you, Paul. And also, just before we hand it to Paul, we will have questions throughout the presentation. Feel free to ask anything in the chat, and we'll either do questions during the session or at the very end of the presentation. Thanks, Paul. Over to you.
Thanks very much, Valerie, for that very kind introduction. Thanks, Haley, for the invitation to join in the session this month. I'm really pleased to be here. All right, if everyone holds on for just a moment while we take care of a little technology transfer. If all goes well, you should be seeing my screen. Is that coming through now? Just is my screen share coming through?
Yes, Paul.
Okay, great, thanks. So we're talking today about the very dry sounding but highly exciting topic, genuinely, of evidence-based design, borrowing a term from our colleagues in the medical profession. We do a lot of work here at Atelier Ten, and I think all of you do too, informing ourselves about what aspects of design will improve passive performance. That's the topic today. Just the overview, so I'll introduce myself and briefly the practice I'm with Atelier Ten, so you can understand the context of where we come from. We'll then talk through high performance design outcomes, focusing on daylight, then thermal comfort, then kind of energy, and also associated with that kind of peak heating and cooling loads. And all of these will be illustrated by a series of case studies. The things I hope we all take away from this are just a review of what are key passive performance design elements, and there's more than we're talking about today, so feel free, if you're passionate about other things we haven't talked about, to raise that in the questions. We'll talk about those when we finish up. I hope you take away an understanding of some of the critical kind of passive design evidence, understanding kind of what are key metrics and what are preferred outcomes, and also which metrics are appropriate to answer which questions, because it's sort of horses for courses in analysis. I'll talk a lot about a multi-parameter analysis, how we look at different performance outcomes in combination to understand how we balance kind of outcomes through better design. And one of the ongoing discussions will be kind of working our way through data, how we represent data, how we interpret data, how we draw conclusions from data. Just a brief introduction to Atelier Ten and myself. Thank you again for that introduction. So I'm trained as an architect. I've always worked as a sustainable design consultant with sort of 1 foot each in the design world and the analysis world. I joined Atelier Ten out of architecture school when we were a sort of office of 20 people in the UK doing sustainability as the front end of building services design. We've since grown to 300 people in 11 offices, where most of our work globally is sustainability focused. We still, of course, do building services in the UK, but we have been focused on sustainability for 30 plus years now. And again, working very much in this space of providing analysis to inform ourselves and entire design teams about how to shape a more sustainable world. We, of course, spend a lot of time beyond just kind of the science-based technical sustainability. We are fully committed to a more sustainable, many more sustainable futures. And that's what's so exciting about practicing today, is we are talking about many things beyond just energy and water. Thank heavens, they all matter a lot. And what we do at Atelier 10 beyond, I think, kind of beyond compliance, we might say, is at a critical step, I expect you are mostly all doing as well, is starting with, talking about what does sustainability mean for the project, establishing a vision and goals, and then doing the fun brainstorming bit, how to use design to solve them. And we'll see that in this analysis, that there's no single way to analyze kind of high performance outcomes. It very much depends what we want to achieve, which goes back to what is this a building or a place about. That then sets the context for how we might design it, which sets up the questions that we can answer in part using analysis. And what makes us different? We analyze. Other people analyze. I think we do a good job of doing analysis early on when it can meaningfully shape project outcomes. So let's start with daylight, something that seems very evident. We have all grown up kind of inside and outside and understand daylight. I want to make the point here that there are many different ways to measure daylight. They are all useful. They're just useful for different things. So first of all, just when we talk about daylight, often we are talking about illuminance, which is the daylight that falls onto a surface. That's the daylight that normally we can't see, except of course when it sort of hits things in its way, like a surface, which then reflects light to us. So the light we see coming off a surface is luminance. We'll talk about that in a moment. But for most daylight, we're talking about illuminance, the amount that lands on the surface. When we measure illuminance, when we simulate illuminance, we're trying to figure out how a building might work, how much illuminance there might be. We need to think about what are the conditions we're simulating. Are we simulating on an overcast day or a clear sky day? Is there a sun? Is there no sun? What hour, what day, what month, what season? So it starts to very quickly become a slightly complicated question. When we talk about daylight, what are we talking about? We can answer this, and you'll see that in a moment, using basically simulating some hours of the year or all hours of the year, simulating daylight, typically now using an analytical engine called radiance. But before we had computational power, we sort of simplified things by saying, well, rather than calculating exact daylight, let's calculate the proportion of daylight that's available inside a building relative to outside a building. That's essentially a fraction of the sky view from any point in a room. We've got a fraction of the sky view, we know a fraction of the daylight available. That method's called daylight factor. And that is the old-fashioned hand calculation method, and it's still useful as a rough gauge of how much daylight will get into a space. It is particularly useful when you're designing for a constant sky, where there's not a sun moving in and out and up and down and around and sort of complicating what the daylight will be like. And as it so happens, the UK has got a lot of overcast days, as does most of Northern Europe. So it's still a very useful reference in overcast sky conditions like Northern Europe. And there's rules of thumb about how much daylight's appropriate. 2% is a solid target in the UK. In Australia, with our very bright, typically clearer skies, 2% daylight factor, 2% of the daylight outside coming inside is often too bright. So we have to appreciate that rules of thumb when we move them from one country to the other are not always relevant. So you'll see daylight factors calculations pop up here and there through some of the analysis we show, because it's quick. It can be calculated geometrically. You don't need to simulate daylight. A newer daylight metric is called daylight autonomy. This looks at a point and calculates the number of hours at that point where the daylight is above a certain level, where you have enough daylight to do a job. So we can think of this as daylight effectiveness. Now that's for a point. If we look at many points across a floor or an area, we can talk about spatial daylight autonomy. And now the metric is spatial daylight autonomy. So it's what is the percentage of floor area that meets a daylight criteria, which might be 300 lux, and also meets it across some time span, which would typically be occupied hours of a building. So a spatial daylight autonomy target might be 50% of the floor area has to be daylit above 300 lux for working hours. So that gives you, kind of how effectively is an entire area daylit. So that's a solid metric that's used increasingly by our international green building certification programs. It's referenced by WELL. It's now one of the standard reporting methods for Green Star as well. Now, one of the things that's critical to understand about daylight is too much daylight can be as problematic as too little daylight, especially if you're working on a screen where the screen gets, as our eyes kind of shut down in response to brighter and brighter conditions, our computer screens, which can only get so bright, start to look dim. So another metric that's come along more recently recognizes this, and this metric, or useful daylight illuminance, the UDI metric, looks at hours of daylight above a minimum and below a maximum. So you can think of this as kind of good daylight effectiveness. And it has the same structure as spatial daylight. We can look at number of hours across the year, a working year for a point in space, or we can look at the spatial version of useful daylight illuminance and look at the percentage of the floor plate that has daylight within a criteria over time. This is our preferred metric for office workplace analysis because it shows us high quality daylight. It's not too dark, it's not too bright, it's, it's Goldilocks, it's just right. And there is some flexibility to adjust the minimum and maximum thresholds to suit the program. Now I'll show why would we use different metrics. A little bit is to respond to different rating criteria, which suggest different things, and also they tell a slightly different story. So this is an analysis of an urban infill project in Melbourne, as it happens, looking at daylight levels for the building as kind of calculated under current daylight conditions. It would be the tallest thing built around it in the short term. If we look at kind of the Green Star minimum of daylight requirement, which I think in this case was a daylight factor of 2% or more than 40% of the floor area complies, not quite 60% complies. So, it gets 1 point and doesn't quite meet 2 points. To put that in context, it also meets best the Melbourne-based Victorian kind of green building assessment tool, daylight factor target. So it looks like we're doing well. But if we factor in kind of potential future building around this site, then we start to see much lower levels. So, gosh, are we too low? Because these buildings essentially block sky view. We don't get a lot of daylight in. Daylight factor says we're not doing very well. But if we switch to a more sophisticated metric like spatial daylight autonomy, which relies on calculated daylight levels, that includes reflected light off of adjacent buildings, we see actually it's doing all right. With spatial daylight autonomy with a minimum threshold of 200 lux and aiming to meet 40% of the time, then we actually do pretty well. So different metrics will give you different levels of information, noting that we're trading off, in this case, time through more computational intensity to get this answer, which helps us give us a more nuanced picture of daylight level that can be achieved here. Now, I've showed you examples for workplace buildings where there's a pretty clear sense of what is good daylight. I just want to point out that there is no good industry-agreed daylight metric for residential buildings yet. One of the reasons for that is daylight and residences want different quality of daylight for different things. I, for example, like to sit in the sun on a chilly, wintry day, but I like to sit in a relatively low-lit environment when I'm working from home and I need to have a computer screen in my field of view most of the time. I don't want to see bright surfaces. I don't want to see direct sun. So that's one of the challenges of residential buildings. We need them to be all things, well, not all things. We need them to serve a lot of different outcomes. And kind of the relatively uniform daylight of office is not appropriate for residential buildings. So this is a big challenge because our building codes want us to have daylight metrics for residential buildings, and honestly, there's not a good one. So we struggle with this, as does the industry, to come to consensus on what is good daylight in a residential building. That's enough on my side on that. I'll just finish out by saying that the kind of parallel kind of key concern of visual comfort is we talked about illuminance, the quantity of light coming into a space and landing on a surface, landing on your desk. That's one measure of daylight. That tells us, do we have enough light generally in the right distribution? Luminance, or the light that comes off the surfaces, what we actually see, tells us how visually comfortable are we. So if we've got, and the concern we have is if we have very bright surfaces adjacent to very dark surfaces, if we have high contrast, our eye struggles to adjust itself to accommodate both. In short, our pupils will shrink, and our pupils will respond to the brightest surface to protect our eye. So it responds to the bright surface. So the relatively low light surface becomes dark and hard to read. So glare, which is when your eye's struggling to deal with kind of bright and dark light, is something we care about a lot in workplace. We don't care about it so much though in a home or in a lobby of a building where a bit of bright sunlight adds animation and life to light. So the other thing I'll note just computationally is that calculating glare, there aren't as many metrics. So there is one now called daylight glare probability, where you look at basically contrast ratios within the field of view and percentage of time that those contrast ratios existed, and then we can calculate daylight glare probability. This is a very computationally intensive process. It has a very specific view associated with it. So there's a lot of data to wrangle, and it's quite a complicated metric. So we do daylight glare probability calculations. We do use glare evidence in our design process, but we do it sparingly. We can use useful daylight as a good proxy for glare, even though it's not a direct calculation of glare. All right, I'll just pause for a moment. Have any questions come in, burning questions on daylight that I can answer before we move on to thermal comfort?
We don't have any questions in the chat, but if anyone listening has got a question regarding to that, please post it now or leave it for the end of the presentation.
If there's no burning questions yet, I'll keep on cracking, but please don't be shy with questions. I love to answer questions. So we'll move on to thermal comfort. So just a reminder that thermal comfort is not just what is the temperature of the air, which is what a thermostat or thermometer on the wall will tell us. How comfortable our body is very much influenced by, is there air moving past us? How much clothing are we wearing? Is it a hot, sticky day or a very dry day? And also, are we in a hot, radiant environment? If we stand or sit in the sun, we will warm up very quickly, as you know. If we move into the shade, we'll cool off very quickly. So thermal comfort is a multi-parameter analysis all by itself. Fundamentally, we're trying to design for what we might call thermal autonomy. Like we talked about daylight autonomy, we're looking for thermal autonomy. We want to create environments where it's comfortable most of the time. We don't need too much supplemental heating or too much supplemental cooling. Now, how do we measure comfortable enough? Lots of different ways. So there's, again, metrics. We choose metrics for comfort based on the need. The most traditional way of calculating comfort is something called predicted mean vote, or PMV. It's an international standard. It factors in inputs for clothing, wind, kind of airspeed, temperature, humidity, met rate, how hard you're working, all sorts of things, and kind of predicts what percentage of people will be comfortable for that given condition. So it's a all-purpose tool, but it is very biased in that it was the data sets that tell us who will be comfort were generated in the 1960s, mostly using males between the ages of 18 and 25, basically college students who are looking for some money, so they did the research in comfortable and uncomfortable environments. So these data sets are gendered and out of date and only good really for a comfort condition where the assumption is you are working at a desk. So if you're doing workplace comfort calculations, PMV is okay, noting that it is gender biased. There is another version of PMV called Adaptive Thermal Comfort Method, developed in no small part through leadership of Richard Didier, who's based here in Australia, here in Sydney, at Sydney Uni. This is a version of the PMV standard that acknowledges that people feel more comfortable when they're near operable windows. Even if they don't use them, interestingly enough, they feel more comfortable. They will be more comfortable if they use them. Now, this method makes a bunch of assumptions about workplace, so that and kind of limits some of the inputs and outputs. So it's good for workplace comfort calculations, but it's not so flexible for use outside of workplace. A third comfort metric was developed for outside conditions. This is the Universal Thermal Climate Index. It is not described by an international standard. It's described by basically some scientists who think it's a good way to measure outdoor comfort and have done so rigorously, but it's not an international standard. It's good for outdoor environments, and we use it for describing comfort in outdoor environments. It comes with the risks, though, of it's not an international standard. And notice we've talked about workplace comfort, we've talked about outdoor comfort, but we haven't talked about indoor-outdoor comfort, we haven't talked about home comfort, we haven't talked about a lot of everyday environments. So we've got tools, but they have to be used with caution outside of very defined places. An example of kind of workplace comfort of evidence is this is a study we did for an indoor-outdoor place. It's a sheltered, essentially, marketplace, and we looked at comfort from outside the front door, where you're under a shelter or under an overhang, but you're still outside, sequentially moving into a big hall that provides more and more shelter as you move in. And we calculated using the UTCI method, Universal Thermal Comfort Method, And for each of the points, we looked at it with and without air movement. The fundamental question was, how do we increase comfort in this hall based on what the hall is? And we wanted to explore how much do fans help with comfort. And the point here is that fans sometimes help. In the winter, they don't actually, they work against us. So we want to be able to have fans on-off switches, which seems, like very obvious. If you've ever lived someplace where you had control of a fan, you turn it off when you're too cool, you turn it on when you're too hot. But for great big buildings, it's important to run these things to ground and make sure it's worth the not insubstantial cost of putting in fans on controls. So just the point is we're looking at these and doing comparisons, which is what the real power of simulation is about, is comparing different cases. Another way we looked at this is, rather than looking at all the hours of the year in a bar graph, we looked at all the hours of the year spread out in what we call a carpet plot. Kind of January is over on the left side. You can see my cursor over here. And the hours of the day run from morning up to midnight. So morning to midnight, morning to midnight. So January, February, March, April, May, June. You can see June here. The colors are dark blue, representing cold. And as we get back into November and December, we have hours in the middle of the day where it's bright and sunny and hot that are yellow and orange. So graphically, I hope these plots show that. You can see here in the no shade environment, it's pretty hot in the summertime and pretty cold in the winter night. Exactly what we'd expect. And you see the distribution across the year. And as we move into the space, we see the shed that we were analyzing do more and more work to stabilize comfort. And just again, comparison, this is a no movement scenario and a scenario with air movement. So in the summertime, if we add air movement, we get much more effective cooling. But if we keep the air moving, we keep the fans on, we end up with overly cold conditions, making the point that we want to be able to control it. That's an outdoor comfort scenario. Now I'll talk about an indoor comfort modeling scenario. This is work we did in collaboration with BVN Architects several years ago for a student accommodation building at ANU. Comfort is a critical performance outcome for this project because there is no air conditioning. There's heating in the winter for basic safety and keeping everybody from hypothermia, but there's no AC. So the building is providing passive design. Also, just in context, this had lots of sustainability ambitions, including One Planet Living targets and other things. It's a timber structure. It's a really, really beautiful building. And it was all designed and delivered and open for students to move in within 24 months. So we had to move fast. The question was, how much passive comfort could we get out of the facade design? And the first thing we had to do was essentially describe how we measure thermal comfort. Because there's not a good metric for thermal comfort in residential buildings, or there hasn't been until recently. We'll talk about that in a moment. So we said the logic we used is we can look at PMV, but we'll also look at comfort overnight and look at the number of hours above 27 degrees centigrade, for the reason that during the day, if it's hot, students can leave their room and go to the library or go to a classroom building or go someplace with air conditioning and be comfortable. In the middle of the night, everything is closed, all they can be is in their room. So that's when comfort really matters. So we want to see how comfortable it is overnight. We were also optimizing the facade, of course, for daylight, for low energy use, and for natural ventilation. And these things are often in opposition to each other in terms of what you want the facade to do. Rather than model every room, which gets computationally very expensive, we started modeling typical spaces. And we described them kind of generically. We didn't try and, for every room, we'll model a general room. We'll look at essentially how big is the window, how big is the shading overhang, the shading cowl around it, and a few other parameters around glass performance and wall performance. So we can quickly generate many, many options. We did this using in a Grasshopper environment, using all the tools that most of you know. And the point is, for all of our inputs, which are on the left, which were, we modeled a single room, we could orient it 4 different directions. We had different shade depths, we had different window to wall ratios, we had 2 different glass kind of light visibility parameters, we had different amounts of shading through the glass, and we had a basically fan off, fan on scenario. We modeled thousands of combinations, and in this funny looking plot, kind of the inputs are tracked on the left, the outputs are tracked on the right. The outputs here are the daytime hours above 27 degrees, the nighttime hours above 24 degrees, and then the amount of energy used. Are we compliant with ASHRAE 55, that other comfort metric? And Are we code compliant? And do we have good daylight autonomy? So you're starting to see some of these metrics show up. Each line in this plot represents one unique combination of inputs resulting in outputs. And we can drive through the data by kind of selecting all of these solutions that fall through, say, in this case, an ASHRAE 55 outcome of 2 or below. We want to be code compliant, so below 100% of BCA light energy use, and we want to have good daylight. Daylight autonomy is 70% or higher. That limits the number of solutions, and now we can follow these lines through to find combinations of design inputs that deliver these outputs. So we call this multi-parameter analysis. We call this particular data representation tool a parallel coordinates plot. Each one of these verticals is a coordinate, so showing them in parallel. And by isolating the inputs or isolating the outputs, we can get very specific guidance on what works. This is the evidence that we give to ourselves, the analytical evidence we give ourselves to know what works and how do things work better. We'll see more of these, so you don't have to understand it all from this graph here. Suffice it to say, through this process, I'm working very hard to test many different window combinations with the data we had. We were able to achieve substantially better thermal comfort in this project than ANU was expecting. We were able to drive down energy use. We were able to deliver good daylight. We were also able to kind of value engineer a substantial amount of the external shading off of the building because it wasn't delivering that much. The windows were right sized, the window glass was high spec, and the shades weren't as needed. So some were kept where they were providing high value on certain orientations, but a lot of the rest were removed. That allowed $2 million from the facade to get relocated to interiors and improving the indoor environmental quality. And also it just removed material from the project, which reduces embodied carbon. So it was a big win for the project. Now, I said before, how do we measure comfort in residential buildings? There is a new-ish standard that's come from the UK. It's not technically a comfort standard. It is a design methodology for the assessment of overheating risk in homes. And what this standard suggested is very similar to what we had modeled in that prior case. We want to know, are there temperatures above which there's a risk of overheating in homes, and people getting sick from it being too hot. Now, this is a UK standard, which is got a different climate expectations. So we took the first of the two metrics in this standard. The first one is kind of basically a statement that for no more than 3% of occupied hours, our living spaces, living rooms, kitchens, and bedrooms, are not to exceed an upper temperature limit. And that upper temperature limit tracks with outdoor conditions. So that's a basic, not too hot metric. We have, because of our Australian climate being more extreme, we've suggested a higher percentage of hours should be allowed. The second metric is a nighttime metric. Again, bedrooms are not to exceed a maximum temperature of 26 for more than 1% of hours overnight. This is straight up, regardless of outside temperature, don't exceed. And we've suggested in Sydney, Australia generally, we have a slightly higher allowance, again, acknowledging our higher base temperature. We're more adapted for a warmer climate. So this is an emerging standard from the UK. It's very focused on residential. It's very focused on passive design. The simulations or the calculations of performance here assume no air conditioning. So this is a straight up calculation of space temperatures delivered through passive design. So now this is the standard we use in residential buildings when we're figuring out, are they performing well? So we can take a big floor plan and do now a more sophisticated version of what you saw us do several years ago and take complex units, simplify them and run thousands of variations so we can understand as the architects are designing, where do they get value for money in driving up passive design performance. So for example, we took a group of units that shared a similar typology. We modeled thermal comfort in this orange box area, which is the area adjacent to the window, to understand what is thermal comfort like in there. The rest of the units, it's far enough back from the window, it's going to skew results. So we just look at this limited bit, and we modeled overshadowing from adjacent buildings, all sorts of performance parameters to understand thermal comfort and other outcomes. So you've seen this format again. The inputs are on the left, the outputs are on the right. You see we're modeling more inputs now. We've got a bit more computational power, more outputs, and the outputs include TM59 factors based on the room time. And now the analysis we do looks at for all the different combination. What is the current design? How's it doing? It's doing all right. It's coming in, 9% of hours are above 1 degree for a normal room, which is pretty good, below our 10% threshold, but we know we can improve it if we, in this case, change the glass performance. So we drive through the thousands of simulations, we choose the current, we choose a few improvements, and we can map them out here to see how they perform. Now, this analysis is also showing us peak cooling load, peak heating load, and some other factors. We can also see what has minimal impact. In this case, for this unit type, the R value of the insulated wall, the little bit that there is, had little impact. So we know we don't have to worry about that one, which is very helpful. Another interesting thing we looked at in this particular analysis was the kind of window. And one of the struggles for especially west-facing rooms is how they get rid of heat once the sun goes down. Mostly that's flushed out through natural ventilation. A typical awning window like this just doesn't allow that much ventilation. It fights to get in and out the bottom portion. It's not a very effective way to ventilate. Different kinds of windows ventilate more effectively. So double hung windows, where there's a gap at the bottom and a gap at the top, have a lot of air movement. Pivot windows that pivot in the middle have more effective ventilation rates. So one of our findings was change the window type. You can cool off rooms faster that face west and achieve a higher number of comfort hours. So a very practical thing. This was looking at different kind of conditions for different windows, and you can see here in a different kind of annual representation. Awning windows with 10% open area versus 30% open area, the 30% open area windows cool off faster. So we were able to, with a very minimal kind of and very DA compliant design change, get substantially more hours of comfort for just a window type change. Something I want to highlight here is we're also modeling regularly, not just for current weather, and we buy specific weather file types called TMY7. It's the 7 most recent years of weather, which are 7 of the 10 hottest years on record. We use this historical weather as our baseline, not the reference files, which are now out of date because they're based on weather from the 80s, 90s, and 2000s. That's not relevant anymore. So we use current weather. We also model with future weather. I just want to make the point that a typical facade in a residential building with a code-compliant facade, typical code-compliant facade with current weather, let alone future weather, leads to a lot of hours of not too much comfort, a lot of hours of discomfort. A high-performance facade will deliver substantially more comfort. And I hope that's, again, the point here is I hope that's evident just through the graphic, the way we're representing the data. Each dot is 1 hour of the year. Green is comfort. Yellow and orange is too hot. Blue is too cold. It should be pretty evident what's going on. This is a critical part of data representation, is using graphics that intuitively communicate kind of outcomes and putting them in comparison to each other so you can see how one case performs against another case. Moving on toward the end of the things we'll simulate, so we have time for questions. Energy and peak thermal loads. This is straight up, old school ESD, understanding energy and kind of mech size. Just in this case, we'll talk about mech size first. We look at kind of annual cooling load, annual heating load, and we'll also look at peak cooling loads, like what's the instantaneous demand for cooling, essentially how is your system sized. And we'll try and target peak cooling loads in the zones adjacent to building facades of 80 watts per square meter or lower. So 80 watts per square meter of cooling needed to basically keep people comfortable for energy. And this is an energy metric. This kind of simulation assumes that there's air conditioning, so it's more appropriate for office buildings, is appropriate for residential, but needs to complement the passive design calcs you saw for the TM59 simulations. We also calculate annual energy use for buildings that they're compliant with Section J or BASICs, depending upon what it is, and note that there can be slight baseline differentiations between kind of an electric building baseline and a gas building baseline, although that difference is going away. So these are more straight up outputs we measure against. And when we look at energy, especially for office buildings, we will sometimes model a chunk of an office building, sometimes we'll model a whole floor. If it's an irregular floor, like this building we've modeled recently has got one face of the building that's mostly solid because it's effectively a party wall adjacent to another building, and 3 sides that are glazed. So we model the whole floor to understand how it performs overall in a Section J calculation. But notice we're just modeling one floor. We're not modeling the whole building. We're trying to get early in the project a sense of how will a typical unit respond, so we can understand how the whole building will respond. Again, you've seen these kinds of simulations. I'm just going to flick through these, not to say how this building works, but rather to show you that one of the interesting things analysis can tell you is how do inputs correlate with outputs. For example, window to wall ratio, which is highlighted here, and the red and blue is correlated with window to wall ratio. The high window to wall ratio is the blue lines, and lower window to wall ratio is the red lines. You can see from the results that there is some correlation. There's a bunch of blue lines at the top and a bunch of blue lines at the bottom, but it's not a hard correlation. There's a lot of mixed up solutions in the middle. If we look at, this is a window to wall ratio for the south facade, you can see it doesn't really affect performance. U value is not a driver of the design. You can see there's red and blue solutions all throughout. So it matters, but it's not going to drive design solutions. That's essentially window framing performance. In this case, solar heat gain, similarly enough, is not a major driver of building performance outcome. It matters, but it's interesting that it's not the dominant one. In this particular building that we model, R value actually matters quite a bit, as you can see here from these two scenarios. Horizontal shade depth matters a lot, and the vertical shade angle matters a little. So not to say they're not important, but just when we realize that if we're going to make big design decisions, some are bigger than others. The final point I want to make using these graphs is that when we look at optimizing, it's very important to understand what are we optimizing for. So I'll just go through some scenarios here. This is a scenario that we're looking at through all the solutions that looks to, beat section J and minimize cooling load. Minimizing cooling load gets us the smallest possible HVAC system, which has certain advantages. So here's a design solution set on the left that gets us the lowest possible cooling load. So low window to wall ratio, lower U value, lower solar heat gain coefficient, lower R value, more or less the things you'd expect. Although in fact, you can get it with a higher R value. And deeper shades, that gives you the lowest, gives you a good solid performance. But interestingly enough, there's no option for minimum shade depths. So it's telling us we'd have to have a maximum shade depth if we optimized for this. If we wanted to avoid a costly, more costly thermally broken curtain wall system, that suggests there's certain things we have to do. So you see there's some of these options drop out. If we want to maintain a particular architectural look, within this case, the 450 millimeter shade depth, we can lock those in with this analysis. And that tells us that some of these, we've got some flexibility in some of these, others we've got less flexibility. We might want to maintain a deeper window to wall ratio, and that tells us that other things are possible or not possible. So again, the data is useful to finding patterns in the design and running through scenarios. And these are all pre-simulated essentially before the design was locked in. We worked with the architects to identify the range of the possible for the shading performance, for the window performance, for the rest. And then this provides the evidence that we test on an ongoing basis as architectural options are developed. And again, I'll just go through scenarios here. When we optimize a building, we rarely optimize for one thing. We usually talk through many different potential outcomes and understanding how the design would change and respond to them. So in this case, if we're looking to avoid, we've talked about this before, actually, avoiding the expensive thermally broken curtain wall system, that would lead to certain design outcomes being more preferable, or lowest peak loads, or best in class performance without super framing, which is our term for internal insulation, best in class for 450 millimeter shade depth, and so on. So all these make the point that there's not necessarily a best outcome, there are better outcomes. And when we do design optimization, we work our way systematically through what are the outcomes we're after, talk about the pros and cons, and resolve the best possible set relevant for the project. In this case, this is a commercial office building. Some of them are more obvious, some of them are less obvious. We need to work them through. I just want to make the point that the danger of sort of one button, super simplified modeling processes is that they don't always make it evident what you are optimizing for and really what are the outcomes that matter for the project. So I hope this series of examples has shown that there's lots of things to optimize for, and this is evidence, but it is not the solution necessarily. The design solution is discovered in collaboration and in discussion and in coordination amongst all the members of the design team based on lots of different outcomes. And that's the end of my example. So I hope you've all gotten a sense of what are some of the key passive design performance elements. What are the metrics? How do we measure them? What are some of the preferred outcomes? And critically, metrics are appropriate for different kinds of analysis, especially for different kinds of buildings. You've seen a multi-parameter analysis process and different examples where we can look at how different combinations of building elements work together. There's some insights to be gained from us analyzing them all working together. And I hope you've gotten the sense that data representation is not just to make things pretty, but also it really helps us understand quickly what's going on. We can see patterns, and we can use tools like the limiting factor and the multi-parameter tools to guide us to data, through data, to solution sets that work or provide insights into the project. And then, of course, we interpret them together. What does this mean for the project? Is this right? Just because it performs better from one dimension doesn't mean it's necessarily the right thing to do. That is the end of the formal presentation. So over to everybody on the call for questions. Thank you.
Great, thank you, Paul. We've got a couple of questions already in the chat, and if there's more questions, please just pop them in the chat. Joshua is asking, what software do you use for daylight analysis and thermal comfort, and basically all of the analysis that you've been doing?
Sure. For daylight analysis, we use typically Radiance. Radiance is the engine. We normally use Radiance in a Grasshopper environment, and it's controlled by other elements in the Grasshopper environment, sometimes by the Animal Zoo. We occasionally use Radiance directly from other tools, but mostly we use Radiance in a Grasshopper environment. For our thermal comfort analysis, the analytical engine is normally Energy Plus, again, controlled through other apps in a Grasshopper environment. Occasionally we'll use IES. Normally we would only use IES though if we already have a model existing and it's an office environment, and we don't normally use it for exploratory modeling. We do still quite a fair amount of spreadsheet analysis, depending upon what we're looking at. We often start with spreadsheet analysis. And for example, with UTCI, that's typically done with spreadsheet analysis.
And Caroline is asking, can you do an associated embodied energy analysis?
Yes, and we do. There's lots of questions though about one of the things I think we're all struggling with as a profession is, what are useful methodologies for doing embodied carbon analysis? When can we get meaningful advice out of an embodied carbon analysis that guides a design forward? And I say this having done lots of life cycle analyses that end up saying all the same thing. Let's use better concrete. And in the limited number of cases where steel strength matters, let's use high strength steel because then there's less of it. We're struggling early in projects to give more specific analysis than that. So we're at Atelier 10 kind of reworking how we do embodied carbon analysis and when we do it in order to figure out what's the right working process. Mm-hmm. And a classic one we grapple with early on in projects is very much around facades. If we have facades, as soon as we hang something off the outside of a building, we're using more material. That comes with embodied carbon. If it's a heavy material like terracotta or concrete, or those are the two worst offenders usually, that it really uses a lot because it's not only that material itself, but it's the steel that holds it. Now, an embodied carbon analysis will say, that's nonsense. Don't put stuff outside the building. Just do glass and aluminum curtain walls. They're not great, but they're a lot better than everything else, by and large, for especially for bigger buildings. But all the other analysis we do would tell us, well, you can have a glass and steel curtain wall, but that means you're going to have pretty poor light quality. You're going to have not great thermal comfort, and you're going to have the blinds down most of the time. So why are we even bothering with windows? So it makes the point that it's rare that we would optimize for any given single parameter. We always need to understand these things in context. And what is the purpose of the project, and how important is the human environment? And that will then help us make decisions about the relative importance of energy versus visual comfort versus thermal comfort versus embodied carbon versus peak loads versus whatever. So we can make better decisions based on what comes out where.
Yeah,
thank you. Very long answer to a very simple question. Yes, we can calculate embodied carbon. That can be built into those tools. At the moment, though, we're not, because we're not certain yet that we're getting the right answers. We're not certain we're asking the right questions at the right time about embodied carbon.
No, that's a good point. Question from David Henderson. Is parametric analysis part of A10 standard scope of services? And do you charge an additional fee? And following from this, should we expect any of our ESD engineers to provide the service?
We use, a great question. We use parametric analysis on most projects where there's facade design involved or facade redesign involved. We use it especially early, pre-DA work to make sure we've got the right general strategy for a facade. So it's effectively a version of JV3 modeling as how we use it, and that's what kind of sets the rates for it, sort of. We don't always do it. Clients don't always want to pay for it, and we're not going to do it for free. We're not a charity. Sometimes it feels like it. Clients keep asking us to do stuff over and over, but we're not. So we use it when we can, is the sort of it. But sometimes we don't need to, especially if we have clients that take our advice the first time around. Mostly we know what it wants to look like. So if we can tell them that and they crack on with it, then we don't need to do the analysis.
And another question from another David Moody. How many models like this are being run on a typical project within your standard fee structure? Let's go into the same question. What do you think is effective level of modeling for a commercial office building, for example? Looks to be a number of models undertaken during early design phases to inform facade design, but also assume additional modeling required for validation during later design development stages. Understand these are all very valuable modeling data. If the multiple models are additional, how do you convince a client to the value of undertaking these early design phase models?
Let's work backwards from the value to how we do it. Many of our clients are repeat clients, and we work with them over time to understand that a little bit of time, a little bit of investment in design, not just for us, but for everyone, generates value down the track. It ensures better building performance that leads to higher Green Star ratings and higher neighbors ratings, which directly affects building valuation. It leads to better visual comfort. It leads to all the outcomes we care about. So, and that takes analysis to make sure we are able to get there. So that's the value argument. We do different kinds of models in different stages of the project. So the models you've seen today are all early stage, because this is Architects Declare that we're talking with, and you all are really excited about the front stages of projects where we put together the look and the feel of the building. So this work is primarily pre-DA work. We do sometimes use these multi-parameter models in design development to tune things up. By the time we're also in design development doing whole building models with IES that are also will have parametric elements, but fewer of them and simpler. So we create one kind of model for early stages and different kinds of models for later stages, and we build that into our fee. I mean, this is not bargain basement stuff, pretty clearly. I think is the other way of coming at what you're saying. This is well beyond your compliance-based consulting. Compliance-based consulting is DTS, and do something beyond that only if you have to. This is very much a define a sustainability vision that has better healthy buildings, better environment, better energy outcomes as your starting point, and then use evidence to drive us all toward that. So that takes a client willing to pay for some consulting time.
Yeah, and just a question from me. We do within Architects Declare, we've got firms of all sizes. Some of them, can't engage an ESG consultant early on. What would you say would be the main things that an architect should be considering regarding passive design? What to do if you don't have any tools to hand?
Yeah. A really good place to start is look for case studies, and there are books that have case studies that have rooms described. A room of this big with this kind of window proportion will have daylight about like this, and just working through those case studies, very simple case studies, and the associated daylight quality is a really good way to build up an intuition for how things will work. It's a little bit tedious, a bit like doing your homework, but it really matters. For architects wanting to do some of their own computational design, fantastic. If you're really passionate about something, start there. Because if you're passionate about it, you'll put the time into it to learn it properly. And that's really what matters, to do your homework, to make sure you understand the building science and underpins that kind of analysis so that you understand what the results mean. That's where often the process falls apart. People are excited about generating numbers. They're not as excited about it, but doing quality control on the numbers and putting the numbers in context, that matters a lot. Natural extensions of things that architects are already doing and are the ones that architects tend to pick up the fastest and do well would be embodied carbon, for the reason that you're already controlling most of the specifications and you're already dealing with all sorts of details about material performance. And embodied carbon is essentially a spreadsheet heavy version of that kind of work. Lots of devils in the detail, lots of specialist knowledge that comes with that, but for the obsessive compulsive amongst you, that's a very straightforward way to enter the world of high performance design. Daylight is another very good one. Architects have good instincts on daylight with a bit of study of daylight metrics, daylight performance, and doing some practice models against validated buildings or validated case studies. You can build up your experience and do your own daylight modeling. Just take it one step at a time. Don't try to do too much at once. And if you're a slightly bigger practice, my really especially critical advice is always have two people who can do it. So you can discuss how to deal with hard stuff, and someone can do peer review and quality control, or peer review and quality assurance. That's probably more for the bigger practices, because it's a really stressful situation to be the one person in a practice who can do something, especially when you've got to make a bunch of assumptions about the analysis at hand.
Thank you. A few more questions coming. So Nikki is asking, there's a huge amount of simulations in these studies. How quick is quick when it comes to getting quantifiable comparisons?
So is that Nikki Parker? That's you, Nikki Parker. G'day. Good question. Sometimes, we always calculate number of simulations because we know for one of those apartment box simulations, each simulation is going to take a minute or two. So if we've got 1,000 simulations or 2,000 simulations, that's thousands of minutes of simulations. That's running into days, depending upon how many we run. So we do try and limit that. But you can set a computer to run simulations over a weekend or overnight and come back and deal with the data the next day. The bigger time sink is going through the data to make sure it's valid, it's accurate, and it almost never is the first few times. There's always something that's not working properly. And the second biggest time sink is, how do you tell the story of how the building works? How do you find the lines in the mess of spaghetti that make it evident, this is the thing that is driving performance, and here are the best options, or knowing what your clients care about, avoiding this kind of something, absolutely having that kind of thing. How do you describe the things that work around that? So what's the design story and the design advice that comes out of all this data? So the time goes into interpreting, essentially. So that's where the time goes. The computational time matters, but it's mostly off hours overnight. You just set it and it runs, and when it comes back, then you start putting the time in.
Yeah. So for example, on this project, how long did that take, all the different study analysis on the ANU project? As an example, to do the analysis, the different comparisons, the options?
On that one, when we would do a full simulation run, that was probably, 18, 24 hours, something like that. Because we were running calculated daylight, not daylight factor. So as soon as we calculate daylight, the simulation times blow out. They're substantially longer. You can run a simulation in a few seconds for energy, but it's typically over a minute for calculated illuminance. The fewer the data points we calculate, the faster it goes. So we can trade off, quality for quantity for quality a bit there. Yeah. So again, it comes down to what questions are we trying to answer, determines what kind of calculation we do. We sometimes will do straight up old school daylight factor. They're not great, but they're fast. It's a good first pass for certain kinds of design situations where that's enough to answer the question.
A question from Laura Ten. Do you have any thoughts on the 2022 Section J requirements and how this might affect passive thermal comfort design approach?
Not many, because I haven't spent a lot of time myself looking at this. I know that for basically the non-residential part of the code, Section J is not going to change much, so we're not too worried about that. And I'm not really, I'm not across what's due to change in the residential portion of the code, so I can't comment too much on it, other than I hope it changes substantially, because currently it's not great. It's not very stringent, as you all know. It certainly needs a big kick up the backside. I've shown you lots of Resi optimizations. Interestingly enough, you didn't see a NatHERS column and you didn't see a BASIX column if you're in New South Wales. That's because that's essentially closed software. We can't get access to it. So we end up doing straightforward peak load energy simulations, correlating those against a black box NatHERS simulation to make sure we're reasonably aligned and that we know we'll have code compliant options. But there's a whole separate process to calculate NatHERS compliance and BASIX compliance. It's really painful. I wish that the code software people would open up their software so we could directly access it and calculate NatHERS stars and BASIX at the same time, but we can't. So it's this clunky two-step process for Resi. Which is not the question you asked, but that's my little bit of soapbox there.
So that goes with Elisa Franceschini's questions. Could you adopt your analysis to different energy certifications? So
yeah, we can as soon as they open up the software. But at the moment, the Australian code simulation software for Resi is locked down. For everything else, it's opened up. It's an open standard. Simulate with an hourly program that meets basic requirements like Energy Plus or whatever, and we're good. So that's what we do.
And one last question from Liam Lau. Can you recommend any tools, plugins to substitute multi-factor objective optimization in Grasshopper if it's too hard to do?
I not particularly, in that we use lots of different Grasshopper tools. The tool we use in Grasshopper depends on the question we're asking. Is it about daylight, about thermal comfort, general optimizing? Is it biased towards this, biased towards that? What you're seeing essentially is a bunch of post-processed outputs. So we'll get tables of data that come out of Grasshopper. We take them into other tools, in this case, typically Excel first, to clean up the data and get it into the shape that we want to use it. And then we take it into a parallel coordinates tool. So there's various parallel coordinates tools available. Some of them are freeware. So you can look those up, but it's the parallel coordinates tool that allows you to do the driving through the data. Where the data comes from in Grasshopper depends on what you want to analyze. And honestly, I'm not enough in the day-to-day of that to say I like this animal app more than that animal app. My only general comment is, while the apps are brilliant, they update regularly. There's always bugs. We spend a huge amount of time debugging. We can take one workflow, move it to a new project. Some apps have updated over the time frame and it stops working. So just be super careful when you're using Grasshopper to validate your data, because there's always bugs, and some of the bugs always come from software updates. Always.
Have you used Cove Tool?
No.
No. Okay.
No. We've tracked it. We've looked at it. We've done some experimenting with it. It hasn't provided enough yet for us to change workflows. That said, there are some things that it can do. I know that colleagues of ours across Atelier 10 are looking to kind of do a new generation of, it does a few things very well, that we may switch to using that tool for some things. So we're not early adopters of tools, generally speaking, for the reasons that we want to make sure we get reliable results. And we've been burned enough by new tools that are twitchy. So that said, we're always looking at them. And then when we decide to switch, it's a pretty big investment in switching over. So the short answer for Cove Tool is not yet, but we're looking at it.
Okay, great. I think we may have to wrap up. We've got 1 minute left. I was wondering, is there any wise words you would like to leave the audience with regarding passive design?
Maybe one last insight is something we've been delighted by is, in a way, sometimes we think the most value from an analytical design process or an evidence-based design process comes not from the data itself, but from the rigor it offers when we sit down with the design team to work through possibilities. So when we start describing how big might shades be, how small could they be, what's acceptable, that forces some lateral thinking, kind of very systematically, point by point. And often that discussion moves the design ahead more than a week later results that say, oh, you want it to be this big and have that big, and this doesn't work with that, but that works with that. They will have gotten there already by having the discussion about what might the facade be, and probably we want to think about this because we expect it to lead to that. So the engagement that this analytic process offers is as valuable as the results and insights from the data.
Oh, amazing point. Thank you, everyone. Thank you, Paul. That was an amazing session. Got some comments from a few already on the chat. We will be circulating the recording in a few days' time, and I believe also the slides, right? So yeah, just watch out in your inbox. Thank you so much, everyone. And thank you, Paul, again.